In this video, we're going to talk about an application of integration. In this case, we're going to talk about the area between curves. So, for example, let's say that we have two different functions. We call these functions f of x and g of x. And I want to be able to find the area between these two functions on a given interval. So let's say that I'm looking as x goes from A to x goes to B. In this case, in order to find the area between these curves, really what we're doing is we're finding the area under the top curve, and then we're subtracting out the area under the bottom curve to be able to get the difference of those two areas, which is going to be the areas between the curves, being this. So symbolically, we can compute this by saying, I want to know what is the area under the top curve. That's the integral from a to b of my f of x curve. But that would be this whole area, and I want to subtract out the area under the bottom curve. So that's the integral from a to b of my g of x curve. And using some of our properties of integration, we could compute it this way, but we know that the difference of two integrals can be combined to be the integral of the difference of the two functions, or in this case, the integral from a to b of f of x minus g of x dx. We could compute it either way. The computation will be similar. It just saves a little bit of work in the notation. Another thing to note when looking at these is what happens, like this was an example where both these curves were positive, were above 0. What happens if I have maybe a couple of curves where my f of x curve is something like this, and my g of x curve goes below the x-axis? And I want to know the area between these two curves, the area in this region right here. It turns out that the formula is going to hold, and it's because of properties of negative numbers. That, like we did before, even if I have my integral going from this intersection point A to this, in this case, an intersection point B, that it's going to be the integral of the top curve minus the integral of the bottom curve, because this negative area is going to be subtracting a minus, which will end up contributing to a positive area between these two curves. So let's look at a couple of examples of how we can compute the areas between curves. So suppose we want to find the area enclosed by the function f of x equals x squared minus 4 and g of x equals x plus 2. There are a couple of things that we need to know in order to be able to solve this problem. One, we need to know the points of intersection. Between the two curves. So in our previous pictures, you can see that here our integral was going to go from the value a to the value b, because that's where the two curves intersected one another. Let's go ahead and compute that algebraically. How do we know what the points of intersection are going to be for these two curves? The points of intersection are the place where the x-coordinates and the y-coordinates agree. And so we can set these two curves equal to one another to find out when the y-coordinates are equal, what x values must you have had. So set functions equal to one another, and we get that x squared minus 4, setting the output value of this function equal to the output value of this function, we can find the x value that worked. I'm going to subtract 2 from both sides, so I get x squared minus 6 equals x. Notice that this is a quadratic. I have an x squared term, so I'm going to have to either use the quadratic formula, or in this case, this expression factors pretty easily. Then I see that this can be factored to be x minus something and x plus something. They need to multiply to be a -6 and add to be a negative, so I get x minus 3 and x plus 2 equals 0. I can check this by doing distributive property. Indeed, I end up with that. So this means that in order for this expression to be equal to 0, either x minus 3 is equal to 0 or x plus 2 is equal to 0. So I get two solutions. I get the solution x equals 3 or x equals -2. So now that I've found these points of intersection, I'm ready to set up my integral, but I'm not sure which function is going to be on top or which function is going to be on bottom. So the next step that I want to do is determine the top and bottom function. And there are a couple of ways to do that, but I think that if the curves are relatively straightforward, the easiest way to do it is graphing. Because look back in the example that we had here, that we know that we want to take our f of x curve, in this case was the top curve, and we subtracted out the bottom curve to be able to get our areas between the curves. And we need to know which one is the top and which is the bottom in our example as well. So I'm going to do that by graphing. Let's go ahead and sketch a graph of our function x squared minus 4. X squared is an upward parabola, but because we're subtracting 4, it means that it has a y-intercept of 4, and it means it has x-intercepts of 2 and -2. I can solve that in my head by factoring. So this is my f of x curve. Maybe I should have drawn it in green. F of x equals x squared minus 4. Our g of x curve is just a straight line. It's a straight line that has a slope of 1 and a y-intercept of 2. And I'll draw that one in red. G of x is equal to x plus 2. And given the work that we've already done, we found that the intersection points of these two curves are going to be at the value of x equals -2, which is down here at this point. So this is the point -2, 0, although you don't need to find the y-coordinate. And they're also going to intersect up here at x equals 3. And again, I don't actually need to find the y-coordinate, although it's not hard to plug in my head and see that the x-coordinate is going to be 3. That means that the y-coordinate is 3 plus 2, which is 5, or 3 squared minus 4, which is also 5. So now that we know that our linear function is on the top and our quadratic function is on the bottom, we can find the area enclosed by these two curves. I'm going to set up and solve an integral. So I'm going to take the integral as x goes from -2 to 3 of the top curve, which is x plus 2, subtracting out the bottom curve, which in this case is x squared minus 4, dx. And you might ask, what happens if I got these mixed up? Like, let's say that I flip-flopped the top and the bottom curves. All that happens is that I'll actually get the negative value of this area. So you know that if you set it up incorrectly, you can always take the absolute value of the difference and you'll get the correct answer for the area. But we've set it up correctly, so we don't have to worry about that. I can simplify this. This is x plus 2 minus x squared minus a -4 becomes plus 4 dx. So this is the integral from -2 to 3 of -x squared plus x plus 6 dx. This is a function that's easy to integrate using power rule. So I see that I raise the power and I get negative 1/3 x cubed plus 1/2 x squared plus 6x evaluated from x equals -2 to 3. And this becomes negative 27/3. I'm plugging in 3 for x, plus 3 squared is 9, times 1/2 is 9/2, and 3 times 16 is 18. And then I'm going to subtract out what happens when I plug in -2. So -2 to the third is -8, times a -3rd becomes +8/3. -2 squared is +4, divided by 2 is 2. And -2 times 6 is -12. And plugging that into our calculator, we get our final solution. So our f of x curve is a parabola. F of x equals x squared minus 4. That's an upward facing parabola that's then shifted down 4 units, and it has x-intercepts of 2 and -2. You can solve that by factoring and setting equal to 0. And then our other curve, the linear curve, g of x is equal to x plus 2. That's a line of slope 1 that has a y-intercept of 2. And we can see that we're trying to find the area between these two curves. It's going to be the area of this region. From our work previously, we saw that our intersections are going to be at x equals 3 and x equals -2. So I can label this graph accurately to say that where x equals -2, that's one of the intersection places, and the other intersection place is going to be at x equals 3. And I don't need to know what the y-coordinate is, but I could plug in x equals 3 into either of these functions, and it'll give me the fact that the y-coordinate is going to be 5. And over here, the y-coordinate is going to be 0. But that's all the information that we need to find the area between these curves. We know where to start, we know where to stop, and now we know which is the top function. In this case, the top function is our red function, our g of x function. So the area between the curves is given by the integral from x equals -2, this intersection point, to x equals 3, this intersection point, moving from left to right. And we're going to take the top curve and then subtract away the bottom curve. So in this case, that's going to be x plus 2 minus the bottom curve, x squared minus 4 dx. And notice we could have written this as two separate integrals and taken the difference of those integrals. This just saves us a little bit of pen, a little bit of notation. So working forward, doing calculus, we can see that this is just -x squared plus x, 2 minus -4 is 6 dx. And now I'm going to compute the integral using power rule, raising each of the exponents and multiplying by the reciprocal of those exponents. I end up with a first term of x cubed times -1/3, the negative carries on. The next term becomes 1/2 x squared, again raising the exponent by 1. And then my linear term 6 becomes 6x. The antiderivative of a constant, I'm going to multiply by x, and we evaluate this as x goes from -2 to 3. Inputting 3, we get -27/3 plus 3 squared is 9/2. 3 times 6 is 18. This is evaluating at our upper bound. Now we're going to subtract out the lower bound. -2 to the third is -8 times a -1/3 becomes +8/3. -2 squared becomes 4, divided by 2 is 2. And -2 times 6 is -12. And I can enter all this into my calculator, simplifying this by combining all of these terms, I see that I get 27 halves minus, this becomes negative 22 thirds. Getting a common denominator, I end up with 125 sixths. Notice I ended up with, whoops, sorry, that's a little off the screen. Notice that I ended up with a positive result, which is what you want, because when finding the area between the two curves, you want to have a positive area. Let's look at another example. In this case, we want to find an area enclosed by 3 different curves. So to start off with this, we will need to find the intersection points, but I think that it's more informative just to go ahead and do a graph of each of these functions. So thankfully, a lot of these are pretty easy functions. We see that f of x is the function negative x. That's a line with slope -1, and I'm going to do that one in green. So this is my f of x equals negative x, a y-intercept of 0. And then we have another boring function. Our g of x function is just another straight line with y-intercept of 0, this time with a slope of 1. And then we have a parabola. Let me grab another color. That's been shifted up by 2 and is facing downwards. And we see in this situation, there are actually 3 different regions that we could compute the area of. We could see that the boundary is forming this sort of triangular looking region, and it's actually sort of a curved triangle. There's also this portion that sort of looks like a portion of circle. It's not a circle because it's part of a parabola. And then this other region over here. And we're going to find the area of this top region for this problem. Without that information, you wouldn't be able to find the area enclosed by these curves. Now the key thing to notice is that depending upon where you are along this curve, your top and your bottom functions change. So notice that for the left half of this region, the top curve is our green curve, our h of x curve, 2 minus x squared, sorry, and the bottom curve is the green curve, f of x equals negative x. Whereas once I cross over into this half, the bottom curve becomes the red curve, g of x. So we're actually going to need to set up 2 different integrals because the regions is going to be bounded by 2 different curves depending upon where you are. Let's set this up, but I'm not going to go ahead and evaluate it. To set it up, we need to know a couple of pieces of information, and those pieces of information are, where do these curves intersect? So again, just like step 1 previously, I'm going to look for intersection points. So I need to know, what is the intersection of, let's see, we did f of x in green, f of x and our parabola curve h of x. So we're going to set these 2 functions equal to one another. I see that negative x is going to be set equal to the h of x curve, which is 2 minus x squared. I'm going to add x squared to this side and subtract 2, and I get x squared minus x minus 2 is equal to 0. Again, this is a quadratic. That's just because of the functions that I chose. Let's see, in this case, I am able to factor this. Again, what nice values I have. I might have to use quadratic formula for something like this, but I'm going to get 2 values that multiply together to give a -2 are going to be -2 and 1. And when I add them, I'm getting a -2 and a +1, which is -1. So this gives me solution values of x equals +2 or x equals -1. So these are the 2 intersection points between the green curve and the blue curve. Let's look back at our picture and see if that makes sense. So in our picture, we see that our green curve is intersecting our blue curve in two different places, and we only care about the place over here, which is the negative of these two values, x equals -1. And with that, that's actually all the information intersection. I'm also going to have to find the intersection of my red curve, g of x and h of x. And it turns out this is going to be a relatively straightforward computation. G of x is my function x, and h of x is -2x squared. I add the x squared, I subtract 2. X squared plus x minus 2 has to be set equal to 0. My factorization looks very similar. I get x minus 1, x plus 2, and I end up with solutions of x equals 1 or x equals -2, which graphically makes sense as well. And you can notice this by the symmetry of this figure, that this intersection is at -1, and this intersection is 1. So now we're able to set up our integration, now that I know that these intersection points. I also would have to solve for this intersection point, but I can see easily that f of x and g of x intersect when x equals 0. So that means, do I have enough? Yeah, I have enough room on this page. So to set up the integration, I'm going to take the left half of this region is going to be from x equals -1 to 0, because I'm only looking at that piece of it. And in that case, the upper curve is the blue h curve, 2 minus x squared. And the lower curve is my green curve, which is the curve -x. That's half the area. The other half of the area is going to be given by the curve as x goes from 0 to 1, always making sure my bounds go from left to right, of the upper curve, 2 minus x squared, minus the lower curve, x dx. Or you can also say, this is twice as much work as I need to do. If I just computed half of the region, I know that it's symmetric, so I could multiply this by 2 to be able to get the exact value. And I agree that in this case, because the figure is symmetric, we can make use of that symmetry to do half the work. For the case of this example, I'm going to finish this computation. So in this case, we're looking at the integral from -1 to 0 of -x squared minus a -x is plus x plus 2 dx plus the integral from 0 to 1 of -x squared minus x plus 2 dx. I'm going to integrate using power rule. This becomes -1/3 x cubed plus 1/2 x squared plus 2x evaluated from x equals -1 to 0. And I'm also going to add on the second integral, which is -1/3 x cubed minus 1/2 x squared plus 2x evaluated from x equals 0 to 1. Plugging in the values, I see that plugging in 0 makes everything 0. Plugging in -1, I get -1 cubed, which is -1. This becomes +1/3 plus +1/2 minus 2. This is the area of the left half of the curve. And then I'm going to add on to it the area of this half. Plugging in 1 for each of these values, I get -1/3 minus 1/2 plus 2. And these two areas should have been the same area. So computing this integral, we have the left half plus the right half. And we can simplify each of these. This is the integral from -1 to 0 of negative x squared plus x plus 2 dx plus the integral from 0 to 1 of negative x squared minus x plus 2 dx. It's tempting to want to combine these two integrals, but notice there are a couple of things that make that incorrect. One is that the function on the inside is different, so even if we sort of concatenated these bounds, we would be doing it over the wrong function. We can evaluate each of these functions individually, or each of these integrals individually using power rule, and we get -1/3 x cubed plus 1/2 x squared plus 2x evaluated from x equals -1 to 0 plus -1/3 x cubed minus 1/2 x squared plus 2x evaluated as x goes from 0 to 1. So when we evaluate these, we notice that I plug in the upper bound, which is 0, because I get 0, 0, 0 in each of the terms. And then I subtract out evaluating at the lower bound. -1 to the third is -1 times a negative third becomes a positive third. -1 squared, I get a positive 1/2 minus 2. So this is the evaluation of the first integral. Now I'm going to add on the evaluation of the second integral, plugging in the upper bound, which is 1. I get -1/3 minus 1/2 plus 2. And plugging in the lower bound, I get minus 0, because plugging in 0 for x gives me 0. So notice I get the same thing twice, that this is the negative of this value is the same thing as this value, and simplifying this, I get, what's a third plus a half? That's 5/6 minus 2. I want the negative of that. Plus, over here I get -5/6 plus 2. So this is -7/6, and the negative of that becomes +7/6 plus 7/6 is 14/6, which is the same thing as 7/3. So that tells me, whoops, I'm sorry. So that tells me that the area of the region in this case is going to be 7/3.